Hello, and welcome to Astronomy 100. In this segment, we're going to continue our discussion of stellar properties. Each star has things about it that are easily measurable, things about the properties of the star, size, mass, distance, energy production, and so forth. And in a previous segment, we were talking about the relationship between the appearance of the brightness of a star, the amount of energy that it's producing, and how these two things are fundamentally different ideas, although they're related in many ways. What we're going to do in this segment is we're going to relate the idea of the appearance of the brightness of a star with the energy that it's producing and the distance to the star itself. The problem is that when you look at a star in the sky, you don't know its distance. And if you were to try to judge the distance to a star based on the appearance of its brightness, you could be very wrong. You could assume that a star is indeed close, when in reality it could be very far away and just producing a lot of energy. Or you could have a star that produces very little energy and could be relatively close to us, and of course will look brighter. So the appearance of brightness, the energy that the star is producing, and its distance are all related. So let's see how this idea works. Let's go to our first picture here. If we had the ability to take a star and the light that it produces and watch how that light goes off in all directions, the thing about light that makes it convenient is that it spreads out from the source in a very predictable way. So the light from a star goes off in all directions, and in this picture here, let's imagine this is the light leaving the surface of the star, and it's going off in every direction. And what we're going to do is we're going to introduce a way to measure the light at various distances. And when the light leaves the star, of course, the light is going off like a bubble of light in all directions. And imagine that we could cut this bubble in half. So you're looking inside of this expanding bubble. Let's say that at this particular distance right here, the bubble has reached this far and is this big. And then when the light reaches this distance here, the bubble is now, of course, this big. The light has spread out to be this sphere. And then when the light reaches this distance here, then you have the light spread out to be this sphere. Now, in reality, we're not really concerned with the actual distance, but what we are concerned with is how the distances relate. So this distance from the star we'll call distance 1, and this distance from the star we'll call distance 2, and this one will be distance 3. And what I want you to notice is how each distance is a little bit further away by the same amount. So this is twice the original distance, and this is now 3 times the original distance. Now, when the light goes off in all directions, what we're going to do, though, is just follow one portion of the light. The light, let's say, that leaves the star right here and has reached this distance here. And to make the geometry of this even easier, let's pretend that the light reaches this distance, and we're going to measure it as this square that represents this portion of the light that has reached this distance. So we'll make it a square to make the geometry even easier. And what I want you to notice is that when this same amount of light reaches this distance, which is twice as far away, notice how the square has become larger. And when the original light has reached this distance, 3 times as far away, notice how the square is, again, larger. But how the square becomes larger is the critical part. So here's what I want you to notice. When the distance is this far, the light occupies this area right here, but when the distance is twice as far, notice that the light has spread out to an area that is 4 times larger than the original area at this distance. And notice that when the light reaches 3 times as far away, notice how the original amount of light has spread out to an area that is 9 times larger than the original distance. And so what you'll notice is, if we had the ability to put our eye, and let's say that our eye takes in the entire square, let's put our eye at 3 different distances, and then what we're going to do is judge the brightness of this star by what we perceive at each of these 3 distances. So all of the light goes into your eye, but what I want you to notice is, at this distance here, only 1/4 of the total amount of the light that you got here, only 1/4 of that amount is actually going into your eye. And when your eye is now here, only 1/9 of the original amount is actually making it into your eye. So what that would translate into is the appearance of the brightness of this star at these three different distances would be as such. If you are right here, the light that enters your eye would make the star appear this bright. But notice that if you're now at this distance here, twice as far away, then the original light from the star is actually 1/4 the total amount that you got here, or the star would look 4 times fainter than it does here, because you're only getting 1/4 of the total amount of light entering your eye. If you're now right here, the star would look 9 times fainter, because again, you're only getting 1/9 of the total amount of light that you got here. Only 1/9 of that is actually entering your eye, and 1/9 the amount of light makes it look 9 times fainter. So the idea is that because light spreads out in this very predictable manner, or this predictable fashion, then there's a connection between the brightness of the object, the distance between you and the object, and the actual amount of energy that the object is producing. And so let me show you a graph of how these three kind of work together. The graph on the screen here is showing you the distance between the source, the star, let's say, and the observer. So along the horizontal axis, you see that it says distance, and the numbers are growing as I go from left to right. The vertical axis says brightness. This is the perception of brightness, how bright something appears. And you'll notice that as I go vertically upward, the number is increasing. So here's what the graph is showing. If you were at this distance right here, the star would appear to be this bright. But notice that by increasing your distance, the brightness of the star is changing quite rapidly. It is becoming fainter and fainter and fainter very, very quickly. And you'll notice that the line that describes how the brightness is becoming fainter with distance is following a mathematical function that is what we call a 1/r² dependence. Now what that means is that the brightness that you perceive is becoming fainter by the square of the increasing distance. If we go back to the previous slide, what you'll notice is that when you are twice as far away, the star looks 4 times fainter, or 2 squared, or when you are 3 times as far away, the star appears to be 9 times fainter, or 3 squared. So there's very, very obviously a 1/r² dependence between the brightness that you see and the distance between the observer and the source. Now what I'm going to do is put this into a formula, and the formula is really a lot simpler than it might look. Over here, luminosity is the energy that the star is actually producing, and the 4πd² just has to do with the geometry of the spherical nature of how the light is expanding with distance. But notice the d², that's the important part. 4 is obviously a constant, pi is a constant, and then of course the brightness is your perception of brightness. And to make this formula a little bit easier, because what I'm really more concerned with is that you understand the concept as opposed to calculations, let me put it in this version. And so what you'll notice is B stands for brightness, L stands for luminosity, D stands for distance, and the symbol here means proportional. So the idea is the brightness that you see is proportional to the energy that the star is actually making divided by the distance squared. Now remember, L doesn't change. The star makes a certain amount of energy, and that's what it makes. It doesn't have anything to do with who's looking at it or how far away you are. So L always is the same, but notice as the D changes, it is a d² relationship. So if you are twice as far away, 2 squared is 4, the brightness would be 1/4. So it would look 4 times fainter. If you are 3 times as far away, 3 squared would be 9, or it would be 1/9 the brightness or 9 times fainter. So clearly you can see that the way that light changes its appearance of brightness as a function of distance is related to the energy that the object is producing, the way that that light spreads out over a certain distance, and then your perception of brightness based on that distance. Now, what I want to finish the segment with is to show you a specific example. Let me show you how this concept could be used to help us out in the world of astronomy. So let me show you this example. If, let's say, we were to someday travel to Pluto, and we have an astronaut that is able to land a vehicle on the surface of Pluto. Pluto is a dwarf planet in our solar system, and it is beyond Neptune. The distance between the Sun and Pluto is 40 astronomical units. Now think for a moment what an astronomical unit is. This is something we've used on numerous occasions. Remember that 1 astronomical unit is the average distance between the Earth and the Sun. So what this is saying is Pluto is 40 times further away from the Sun than the Earth is. So this is, the number has been rounded a little bit. The actual number is 39.5, but we'll make it 40 just to make the math easy. So Pluto is 40 times further away from the Sun than we are here on Earth. Now imagine if there was an astronaut, again landing on the surface of Pluto, and then were to look back at the Sun to judge the appearance of the brightness of the Sun based on how it looks from the surface of Pluto. Could we predict what this astronaut would see before ever going there? Well, let me show you how this works. If we use our relationship of how brightness is proportional to the energy that the Sun is producing, in this case, we're talking about the Sun, and the distance squared, what we're going to do is we're going to plug in the number. Now remember, the energy that the Sun produces doesn't change, but your distance is now 40 times further away than the distance between the Earth and the Sun. So if somebody were standing on the Earth looking at the Sun and looking at its appearance of brightness versus somebody standing on Pluto looking at the Sun and judging its appearance of brightness, what we would do is plug in 40 because you are 40 times further away. Now 40 squared is 1600. So what that means is an astronaut standing on the surface of Pluto would see the Sun appear to be 1600 times fainter than somebody standing on the Earth looking at the Sun. So the appearance of brightness follows this 1 over a square of the distance relationship. And so this would allow us to speculate. So here's a final picture I'll show you, kind of cool. This is an artist rendering of what it might look like to stand on the surface of Pluto and look back at the Sun. What I want you to notice is being very far from the Sun, Pluto is very cold, an icy, rocky world, a rocky planet covered with ice. Pluto, at this point, we know of 5 moons that Pluto has. The largest is a moon called Charon, and that's what's shown in the artist's rendering. But then here is the Sun, way off in the distance. And because of the distance, the Sun would look 1600 times fainter than it does here on Earth. So in reality, the Sun would really just be an exceptionally bright star in the sky, as opposed to the big, large, bright orb that we see here on Earth. So the main idea is to understand how the distance and the brightness and the luminosity of an object all interplay together, work together, and how we can make some assumptions and predictions based on luminosity, brightness, and distance. Now in the next segment, we're going to talk about how we determine the sizes of stars, but that's a whole new topic unto itself. We'll save it for that. I hope you'll join me then.